President of Jackson Hole. Welcome. Would like to ask everybody to silence these things, if you would, so they don't go off here. Vibrations are fine. So it's my pleasure to introduce our speaker tonight, Morgan Brown, who, as my wife was reminding me, and I hope I don't embarrass him by telling him, we have known Morgan since he was not this tall, but about this tall. A long time ago. I worked with his father, Rob Brown, many years. So Morgan has degrees from computational and applied mathematics at Rice, geophysics PhD from Stanford, pretty well-known schools, I think. Multiple publications. He's holder of geoscience-related patents. He's worked with a lot of different companies, starting with Hess Corporation back in 2004, and various other ones since. He has his own self-owned consultancy company, Tenax Geoscience. He, in his own words from his CV, says that he's a geophysicist and an entrepreneur in the oil and gas industry. Spent 10 years in geophysical research and development before taking the helm of a seismic processing startup that he and partners sold in 2013. And through his consulting firm with Tenax Geoscience, he provides a range of technology advisory services. So tonight he's going to give you an introduction to geophysics, and in particular, geophysics looking at the kind of thing that we have all the way across Wyoming, which most people aren't aware of, and that is mountain fronts. We have the mountain front right out the window here, and several others, all the way across the state. So you get some insight to that. And so without further ado, I'd like to ask you to join me in welcoming Morgan Brown.
Thanks, John. How's the audio here? Is it good in the back? Okay, great. I'm really happy to see this beautiful venue, but a pretty big audience. So I'm an officer of the Denver Geophysical Society, and we would be pretty happy to have an audience of this size, even though Denver's got 3 million people. Yeah, this is a case study of what's called seismic depth imaging. I'll go into what that is. It's a really interesting example of a 2D seismic line shot near the Rocky Flats nuclear plant that's just to the west of Denver. Excuse me. Yeah, it's probably the best view of buried geology. The geology we see at the surface is but a mere fraction of what's going on at the subsurface. You see from John's cross-section over there, very small amount of that geology is actually exposed. 20,000 feet deep is where the real action is. So this is a really nice example to kind of see under the subsurface very clearly with some new seismic technology. So I'm not going to actually throw a bunch of jargon or heavy math, any math at all, really, at you. I'm going to appeal to your intuition. I kind of assume that you've got about a high school background in physics, and that's about it. We'll see. And actually, I should say this: if you have questions, if something just doesn't make sense, I've timed this talk, so we should have plenty of time to just interrupt me. I don't mind at all. So interrupt all you want, and questions after. Okay, so this is one of the final slides of the talk. But to keep your interest, I'll show it. So what you see is a bunch of squiggly lines with a bunch of nice colors. Oh, okay, cool. So if you're very familiar with seismic imaging, the next 15 minutes or so probably will be boring to you. But if you want to stick around and get some background on how we generated an image like this, then stick around. So this is a depth image of the Rocky Flats seismic line, and it's using reflection seismic data. So essentially it's an echo sounding, very, very similar to echo sounding like a submarine would use with sonar. Those echo soundings are in time. But if you'd want to drill a well into some of this complicated geology, we drill in depth. You need to know that I'm at 8,000 feet, for instance. So the colors on the slide actually represent the estimated speed of seismic waves in the subsurface, the velocity field, if it were. And we use that velocity field to convert the time echoes into depth. And that's really what depth imaging is. So Ned Stern is a well-known structural geologist based in Denver, and he kind of was the spearheaded this Rocky Flats project and recruited me to work on it. Here's his original interpretation of the Rocky Flats line, and it's interesting because I'm a geophysicist, I guess, barely. I'm more of a math software guy, and I know we've got a lot of actual geologists in the audience. So when I look at an interpretation like this, I may think or say one thing. You may think or say many other things. So I would say B, go easy on me when it comes to me talking about geology. But when Ned made this interpretation, he made it working before I got a hold of these lines for depth imaging, kind of working with the conventional time seismic data. He changed his interpretation a lot after he got my depth images. So the main thrust feature, which I guess you would, at this Livingston fault, oops, yeah, this one here, that main fault system, what you would call this is a basement involved wedge structure, if you're looking for context. So I pulled a figure from an article that I found in the APG from Mount et al. They call this particular thing that you're seeing here as a Category 1 basement involved wedge structure. Okay. So essentially, what's going on, and this is me I dumb things down in geology because I'm not a geologist, but essentially this pink highlighted wedge is being pushed from the left, kind of wedging its way into the layers on the right. And it's being thrust up and over the deep layers. So there's actually in this model, there's no deformation on the right-hand side of the model. So all the deformation is kind of limited to the left-hand side. And whatever, the shortening from this end is taken up by that back thrust over there. And you can see there's some uplift. In the real world, at the surface, this is sort of an idealized view. Most of that would be eroded off. There'd be just some remnant of the surface topography. Okay, so this is something I'll probably never ever do again, which is a actual reconstruction in PowerPoint. So this is a sort of a digitization of that model I just showed you. So if you start with the wedge structure, you can divide it up into blocks and faults. And if I translate and rotate those, and I didn't change the shape of the blocks at all. I just translated and rotated them. And you can restore that to a flat line structure. So I have this area almost certainly was not perfectly flat during ancient times. There have been mountains in the air. The ancestral Rocky Mountains have been out here for over 1 billion years, I believe. But anyway, sort of in a cartoon sense, that's what's going on here. Just to show you that interesting, this sort of weird looking structure, geologic structure, actually has a basis in reality. The structural geologists use this reconstruction technique just to see what's possible. Not that I do any of this kind of thing. I focus on other stuff. All right, so let's go back to seismology, getting away from geology. Here's a video capture of a large dynamite explosion taken with a high-speed camera. I didn't make this. Here's a later frame, and you can see that the explosion is mushrooming upward as you would expect. There's a couple interesting little disturbances here, and you can see I've highlighted those with arrows. Let's look at a later frame. It's clear that disturbance is not part of the fireball at all. It's actually a supersonic shock wave, and it's moving at about 6,900 meters per second, which is the known speed of a TNT explosion. So the shock wave expands away from the excited explosion in the shape of a sphere in 3 dimensions. Seismic waves are very similar to shock waves, except we're propagating them through the earth. And they travel down from say you set up this dynamite explosion would generate seismic waves that propagate down into the earth. They don't go at 7,000 meters per second. Typical speed might be 2,000 meters per second. If you get into really rigid rock like limestone or granite, it could be over 6,000 meters per second, for instance. Yeah.
Normally when we shoot seismic, though, we don't do that.
That's this is no joke, and I don't mean at all to make light of this guy. A friend of mine is actually paralyzed, but went from a seismic explosion gone bad. So it can happen, but you're definitely trying to avoid doing that. This is a little bit bigger than a typical seismic charge, which might be 1 to 2 kilograms.
They're usually buried in the hole is plugged, and all of the energy stays in the ground. So,
Unless the guy's doing the backfilling or smoking something, and then geyser time, different kind of geyser. Okay, so Hooke's law is actually the foundation of most of the mathematics of seismology. To remind you of Hooke's law, here's a mass mounted between two springs, and you have to imagine that this spring, the mass there is being held up by an air table. So forget gravity, ignore gravity. So when the spring is at rest here, the spring forces are equal, they're in equilibrium. If I pull the mass off to the right, then the spring on the left is under more tension, and it exerts a greater force than the spring on the right. Oops. Okay. Yep. Oh, did I? Sorry. There we go. So I'm going to plot the position of this mass as we kind of let the system evolve. I've done that. So at time 0, the mass is here shifted off to the right. So if I release the mass, then it basically shoots off to the left until it's stopped by the tension from the right-hand spring. And then the mass travels back to the right, and if you let it keep going, eventually it's going to come to a rest because the spring loses potential energy to heat. If it didn't, then the mass would just oscillate forever. So how does this relate to seismology? This is a really cool animation from a guy he made these animations when he was a grad student at Penn State, I believe. Dan Russell. If you just watch one of the red dots highlighted with the arrows, you can think of those as an individual particle, like that mass that I was showing. And those particles obey Hooke's law. If a force like dynamite is applied, then it causes the particles to oscillate like a spring, and they push and pull on their neighbors. And you don't really think of a rock as a spring, but rocks are absolutely compressible, some more than others. And so in a three-dimensional sense, they absolutely behave like springs. Hence, you can use Hooke's law to derive a wave equation that mathematically shows how these waves propagate in a real Earth. You can see how as these individual particles oscillate, they don't move. The individual particles just go back and forth, and yet it sets up propagating waves of this, compression, high pressure and low pressure zones that propagate from left to right across the screen. And because these are pressure waves, we call them P waves. So when you hear the word P wave, it's either a compressional wave or a P wave. This is another animation by Dan Russell that shows a shear wave, where it looks like the energy is moving. It's a wave moving up and down, but really, any given particle is actually propagating in an elliptical path. So this is called a Rayleigh wave, these are typically the most destructive waves in an earthquake, for what it's worth. Okay, so no talk on wave propagation would be complete unless I showed a slinky example. So I fixed one end of this slinky tightly to a chair and then pulled back on the other end to release it. So we'll watch a video here. There it goes. So you can see the wave travel down to the chair and reflect back to my hand. It bounces back and forth several times. We can look at it at quarter speed to kind of get a better view of the wave. There it goes. So you can see sort of the high pressure zone, and then there's a low pressure zone behind it. And these things evolve, but really, in a sense, all I did was just move the slinky at one point. I didn't actually send that wave down. It sent itself down. Okay, the next thing I did was I moved forward, which removed some tension on the spring, and I repeated that experiment. And you can see that the wave, this is played at 1/4 time. You can tell that wave traveled a lot slower than the previous wave. So we can conclude that waves travel faster down a stiffer or more highly tensioned spring. The same exact analogy applies to rocks. When rocks are under more tension, when rocks are stiffer, a stiffer rock will propagate a seismic wave at a higher velocity. So the speed of seismic waves varies depending on the local stiffness of a rock. Granite being stiffer than, say, unconsolidated sediments out here behind us. Okay, now we can generate an S wave. So instead of pulling the spring back, I'm going to whip the slinky from side to side. So you can see a pulse travel down to the chair and then come back to my hand. But you'll notice that I actually taped two slinkies together here for a reason. So one is metal and the other one's plastic. And something very interesting happens. You notice that when I send a pulse down, and part of that wave gets reflected back. Look at that. The actual, that it has to be true, because the actual wave that goes down to the end could not be causing this. That takes a much longer time to come back. Okay, so this is happening because the two slinkies have different stiffness. The same thing happens when a real wave hits a rock boundary. If the one rock is stiffer than the other, part of that energy that you send into the earth is going to be reflected back to the surface. And that's the whole basis of reflection seismology. We rely on changes in rock properties to reflect some of that energy back to the surface where we can do something with it. So here's a cartoon that shows firing a buried dynamite source into the ground, and we look at a P wave after 0.1 seconds. So I'm only going to talk about P waves for the rest of this talk. Shear waves are cool, but it's too much complexity. So the ground has several layers corresponding to different rock types, different stiffnesses. So similar to our shock wave example, the wavefront expands away from the source in a spherical shape. We're only showing 2 dimensions here, but in 3 dimensions it would be a sphere. So why do I color that wave field red and blue? This curve here plots the particle motion as we might measure with a seismometer. We color code the positive parts blue and the negative parts red. The color codes just give us a more convenient way to display the wave in 3 dimensions rather than trying to plot lines or something like that. So, what we call the color, I call the color seismic amplitude, but it doesn't really, it could represent several. It could represent pressure if we were offshore. It could represent particle displacement. It could represent particle velocity. That doesn't matter. All I'm trying to tell you is that we set off an explosion, and the colors of the wave field tell us where the wave is and how strong it is in the subsurface. Now we can look at the same cartoon wave field after 0.2 seconds. And you notice that the downgoing wave seems to have bounced at that layer. Just like with the reflecting 2 slinky wave, that happened because the wave impinged upon a change in rock stiffness, a different rock boundary. So the bigger the change in stiffness across that boundary, the higher or lower the amplitude will be of that reflected wave. You can see how the amplitude of the reflected wave is less than the amplitude of the wave going down. The second strange thing that you see here is the stretching of that downgoing wave. It's really no longer a sphere. The stretching effect is called refraction. So seismic waves travel at 2,000 meters per second in the top layer and 2,500 meters per second in the bottom layer. So when the seismic energy enters that higher velocity rock, the wave travels further in a given amount of time. So it stretches further than it would if it was just up in the top layer. So let's demonstrate refraction in a really everyday example. So here's the old pen in the glass of the water trick. So the pen itself is straight, but it very much looks like it's bent. So that optical illusion is caused by the refraction of light waves. So light travels faster through air than it does through water, and the light bends at the air-water boundary. So your eye thinks the object is further away than it really is. And so there's a really important physics concept called Snell's law that governs how much bending happens. And the bigger the difference between the velocity and the layers, the more bending is going to occur. Same exact thing occurs in rocks with seismic waves as with these light rays. So why do we care about Snell's law? We have to ask ourselves, what are we trying to accomplish with reflection seismology? I want to understand how seismic energy gets from the surface. I set off a dynamite explosion up there. I want to know how it gets down to the rock layer of interest, the target, and then gets back to the surface. How does that energy evolve? So here I show the wave field at 0.1 seconds and at 0.2 seconds. So I want to understand how a piece of energy on the wave field at 0.1 seconds evolves to get to the wave field at 0.2 seconds. So that's going to tell me how I can trace energy from the source down to the target and back again. So this bent yellow line shows the wave field as it propagates. But how did I draw that bent yellow line? The short answer is I use Snell's law. So Snell's law is simply a statement of the Huygens principle. So we're trying to basically conserve, it's the path of least resistance. It's the shortest path in a travel time sense to get from point A to point B. So you can do this what's called ray tracing to kind of answer the question of how does energy get from point A to point B in the subsurface. And this is a lot more convenient than working with actual three-dimensional wave fields. This array concept gets used over and over again in seismology, and I'll talk about it later. Okay, so the seismometers that get used in most reflection studies are called geophones. And this is a diagram of a geophone. So essentially what we've got is a coil of wire that's suspended from the top of the phone housing by springs. And there's a magnet mounted to the base of the unit. And I think in a real geophone, it's probably an electromagnet. I show here kind of a fixed magnet. But when the ground moves up or down, so the ground, you fix this thing to the ground with this spike. And when the ground moves up or down, the geophone, the housing moves up and down, but the spring and the coil kind of stay suspended because of those springs. So these are much, the concept of a seismometer is not new. These little seismometers are much cheaper and much smaller than a typical earthquake seismometer, but there's a catch. These measure frequencies in the range of 5 to 200 hertz, which is well below what you can hear, but it's kind of the core of what we use in reflection seismology studies. Well, earthquake seismometers measure down to 0.5 hertz. Earthquake waves are much lower frequency than the dynamite waves that we're generating, so they need to listen at a lower frequency and much more expensive. So here's a cutaway view of a standard oil industry geophone. So that it's usually all covered with yellow plastic, but they've just cut it away so you can see the little coil inside. So I've kind of pointed the different components of my schematic to that geophone. If you were to shake that little geophone, you would easily, I've got one at home that I got as a speaker gift actually. You can actually see the spring moving, the coil moving up and down within the geophone. So if you recall Maxwell's equations from college physics, if you move electrons, and it generates a magnetic field. So that's a principle behind an electric motor. Conversely, if you move a magnet, it will induce an electric current. So with a geophone, the magnet is going to move up and down relative to the coil. So that magnet, basically there's going to be an induced electric field. And here I show the direction for a given motion, the little animation moves. It induces a current in one direction. And you can measure the voltage of that current. So if the ground moves in the other direction, moves in the other direction, then the direction of the induced current reverses. So a geophone of this type, really what you want to measure with a geophone is the particle displacement. How does the particle move? How is the Earth moving? What you actually measure here is particle velocity, but it's fairly easy to convert particle velocity to particle motion. The induced current is greatest when the magnet is moving fastest relative to the coil. And that happens at the equilibrium point of the magnet. Here, when it reaches the top of its throw, it's not moving at all. It's at zero speed. The maximum speed is here at the equilibrium point of the spring. Okay, so the first seismic surveys were shot back in the 1930s, and they were what we call single channel. So in other words, you have a dynamite source and you have one geophone. This is back in the day when I can't even imagine how much it cost to make a geophone in 1930s. It wasn't mass manufactured. These were experimental devices. They were very expensive, very cumbersome. They recorded their signals on paper, literally, actually a special kind of paper. Now we record it digitally. But anyway, if you moved your little apparatus around the surface, you could laboriously make an image of the subsurface in that way, and that's what they did back in the day. They quickly discovered that it was cheaper to make geophones and plant them than it was to take a shot. So dynamite was cheaper than planting geophones. So what they would do was basically have, say, 12 geophones per shot. And what you see here is that now, with one shot, I can kind of cover a larger bit of the subsurface. I can illuminate a larger bit of the subsurface with that single shot than I could with just having one channel. You might wonder how many channels are we using in seismic surveys nowadays. Nowadays, they'll use 5,000 to 10,000 channels per shot, and they're shooting seismic surveys over 1,000 square miles or more at once. Huge areas. Another important reason to shoot multi-channel seismic like this is because seismic data is noisy, really noisy. So by having essentially 12 independent measurements kind of the same thing. It allows you to exploit the redundancy in the signal to reduce that noise. Okay, so how do we use seismic data to create an image? We detonate the source. This is the single channel example. The single channel example has the advantage of being really easy to understand. So I'm gonna focus back on that. So we detonate the source and we record an echo in time. So here, this little signal here, we call it a seismic trace. But you can see there's a pulse related to when that wave went down, hit a reflecting boundary and came back. So this is kind of what we measure. We measure this oscillating pulse, like the spring. Literally the spring of the geophone is oscillating a bit. Okay, so yeah, so a single seismic recording for a single shot is called a seismic trace. So if we simply move this apparatus around the surface, we could create a crude image of the buried reflector. And notice that that image is in time. We're interested in an image that's in depth, but that's a big. So and that's a big if. If we have an estimate of the seismic velocity versus depth, then I can convert that recorded time into a depth. And then if I want to drill, I know that's at 8,000 feet. So everything I just discussed, I just showed kind of a one-dimensional example, a nice, beautiful, flat reflector. So what happens if the Earth dips like this? So kind of out here in your area, you've got a lot of buried reflectors that kind of look like this. Pretty complicated geology. So imagine we're going to do a single channel seismic experiment over this dipping geology here. So that one before, if you see the little shot in geophone up there, before with the flat reflector, the energy just went straight down and back up, the stuff that we recorded. But we know that the energy that we record is going to go down in the subsurface. It's going to bounce perpendicular to that reflector, then go back to the surface. But unfortunately, we don't know that a priori. If we knew it a priori, then we wouldn't need to shoot the seismic survey. Yeah, so all we know from the seismic survey, I don't know what the buried geology is. All I know is I recorded a pulse at time t with my single geophone. That reflection could have come from anywhere in the question marks. So how are we going to rectify it? So what if we just went and shot that one-dimensional seismic survey across our buried geology? We would get this. So this is, I wouldn't say, it's not a cartoon. This is an actual quantitative, actually literally in Excel, I went and measured the correct travel time. So this is a quantitative experiment. Now the color codes are coded by, if you remember, if I go back a slide, so I've got the blue, the green, and the red reflector. Okay, so the blue, the green, and the red trace, that comes from those corresponding reflectors.
Is the velocity constant in your model?
In this case, it is. In the next case, it is not. And that's another wrench in the gears. But we can solve it. Okay, so this is what would happen. So if I connected those lines with, connected the traces, the pulses with these lines, we get something like this. It kind of looks like the geology that I expect to see, but I notice that the reflectors are crossing. That is, as any geologist will tell you, this is highly non-geologic. When you see a seismic image where the reflectors cross, literally, as a seismic processing geophysicist, I know that something's wrong. I know that the velocity I use is wrong. I'll get into that later. Okay, yeah. So you bring the true reflectors in. So not only are they crossing, but they're mispositioned. So the general shape that you get is right, but the details are wrong. If you actually want to go out and drill a well, right there, it's in the wrong spot. So I'm going to introduce the concept of something called seismic migration. So when we record a single channel time trace, all we can say is that the reflection happens somewhere along this circle. Okay, and that circle, so it's like earthquake triangulation. I don't know where, I close my eyes, I yell, I hear an echo. It came from somewhere along a circle. Of course, it could have been anywhere. So what we do in seismic migrations, literally, digitally, we spray paint. So I take the amplitude of the seismic at a certain time, and in a digital two-dimensional image, I spray that energy along a semicircle. And PowerPoint is a cool thing because what I can do, I can use these lines that are sort of transparent. And when the transparent lines overlap, they sort of reinforce to make a darker image. So pretty interesting. So you can see here as we sort of do this semicircle process for all the traces that we recorded, we form kind of a constructive image right there. So if a geologist was looking at this image, they would say, well, that looks like it's a coherent image right there. So they would interpret that. Okay, let's move on to the green traces. Notice how the image, the good part of the image, forms kind of displaced from where the actual time traces were. It's because the Earth is dipping. And let's go on to the red traces and interpret it. There we go. So that's the interpretation. Now let's bring the true picture in. And that was the true picture. So that's kind of a magical process. With no knowledge of the actual position of those reflectors, I was able to recover those positions with this process called seismic migration. So that's kind of a magical process. And John alluded to one of the complexities that I'll go into later. Okay, so now we've hit the background. Let's go into the Rocky Flats case study. So the DOE acquired a 2D seismic line in 1983. And they were trying to visualize how or if shallow faults could potentially act as a conduit connecting nuclear waste that was buried near the surface to the groundwater aquifer. So many 2D seismic surveys have been shot along the Front Range, but this is probably the best one that's ever been shot. Beautiful, beautiful image. Also, given the development we've seen in recent years around Denver, it's unlikely that we're ever going to shoot either 2D or 3D seismic anywhere near this area. So this is about as good as it's going to get. So Ned Stern, who I referred to earlier, was my collaborator on this. He tried to recover the data, and he found that the DOE had literally lost the data. So the DOE did not have the data. So he actually had to go to a third party that had taken possession of the data to get it. So Ned coordinated the reprocessing that myself and another party did. 2014, he presented it at the RMAG, which is the Rocky Mountain Association of Geologists, and I've presented it several times subsequently. Here's an area of interest map. So you can see the map of Denver down there with the red line, and then there's the Rocky Flats plant. Unfortunately, because we couldn't get the data from the DOE, we did not have the entire line. We were missing about 3 miles of it, kind of in the up dip part. Actually, the most interesting part, but that's too bad. That's with the pink rectangle. So here's a zoom map showing the lines. There's actually a couple of producing oil and gas wells very close to the line, which it's nice. It helps us calibrate the results that we got with reality. So here's a conventional time migration. So this is now a time image. The blue, instead of red and blue, we have black and white corresponding to positive and negative kind of particle motion. So this is a reef processing done in 2013. And if you remember Ned's interpretation, this deep reflector down here in Ned's interpretation, that was flat. And here it's not flat. It's way not flat in time. There's a huge pull up there. There's a huge pull up because over here, the sediments here are very old high velocity sediments and granite. The velocity of those rocks is much, much higher than the velocity of the sediments over there. So when I take a time measurement, I send energy down to this reflector. It takes a lot less time to get to the target than it does over there where the sediments are much slower. Okay, so time migration, John asked, why did you assume a constant velocity? So I never justified why is this a circle? This semicircle is a constant travel time surface. So migration is just spreading energy from the trace along this constant travel time surface to form an image. So when it's circular, it means that the velocity is the same in every direction. So there's no variations in the speed of sound of seismic waves in the subsurface. And that obviously is not the case at Rocky Flats. So what if the subsurface velocity is not constant? Then in general, that constant travel time surface is no longer a circle. So here's a situation like at Rocky Flats where we've got high velocity sediments, old sediments off to the left, lower velocity sediments to the right. That constant travel time surface is now kind of shifted and warped. It's no longer in general a circle. So if you ran a time migration on this and you assumed kind of constant velocity, then your events would be mispositioned and they wouldn't be focused correctly. So what is depth migration? Depth migration is the kind of the technology I'm presenting in this talk. Depth migration is a technology that correctly handles lateral variations in velocity. So the goal is, how do I compute a constant travel time surface in a variable velocity field? The short answer, I use Snell's law. I basically trace rays in the velocity field from the source point down to every point in that surface, and I can use that to, that's why I have to use rays. So if you just run depth migration but your velocity field is not accurate, you're probably worse off than you would be with a time migration. So you need to have a very accurate estimate of that velocity field in order to get a nice accurate picture in depth of your targets. Okay, so here's the time migration again, and I've highlighted a few areas that I want you to observe. The next slide is the depth migration, but just to confuse you, I've converted the depth migration back to time in order to that we can compare the two images. So I'll flash back and forth. So there's some obvious differences between these two. Certainly there's a lot more fine detail. This is the depth image, time, depth, time, depth, time, depth. The stratigraphic features on the depth image are definitely better focused than they are on the time image. The mispositioning of the events is less obvious, but probably more important from a geologic perspective. So let's go to the next slide here.
What is the depth?
9,000 feet. Yeah, about, that's roughly, that's a Niobrara right there, Niobrara chalk. So I kind of highlighted a couple features of interest on the depth image, and these are just, don't worry about what they are, they're just features on the image. So let's go back to the time image. There's the time image, and I've put those same PowerPoint features on there, and notice how on the time image that feature is over here. On the time image that feature is like, yeah, I can't point, but it's shifted by over 1,000 feet. So there's mispositioning of 1,000 feet or more. If you wanted to drill a target here and you were off by 1,000 feet on your imaging, well, dry hole. And the worst part is you don't know, you think it's a dry hole, but you might have just been drilling in the wrong place. It might be a good play after all. Okay, so just when you thought it couldn't get more complicated, I have to introduce a concept called velocity anisotropy. So you might think, oh, I've got a rock, and surely a seismic wave travels at the same speed no matter which direction you travel. A seismic wave goes through that rock. Wrong. So imagine, as this example, here's an interbedded layer of wood and sponge. So if you squeeze this from the side, basically this assemblage has the same stiffness as wood. If I squeeze it from top to bottom, it's not as stiff as wood. It's squishier because it's got the sponges in between. Same thing applies to rocks. Rocks generally have sort of a bedding plane to them, and there's a preferential axis. So the waves travel faster typically along the bedding plane versus not. And if you tilt the rock, it tends to tilt the axis of that so-called anisotropy. So you don't have to worry too much about it. Luckily, depth migration techniques nowadays can, as long as you can quantify the anisotropy, the migration can handle it correctly. But I'll show you the effect that it has. The left is a depth migration with the so-called isotropic assumption, where I assume that the waves travel the same speed in every direction. And on the right is a depth migration where I assume the velocity changes with direction. And you can see there's some huge changes, improvements in focusing and positioning on the so-called, the one on the right, the TTI. Okay, so next I'll kind of shift more into sort of geologic interpretation. I'm going to show how the depth imaging improved and changed Ned's interpretation at least. So a key component of a thrust feature is the kind of the end of it, which is something called a detachment fold. So imagine if you had a carpet on a wood floor, and you pushed on the carpet, then the carpet would bow up. It would slide across the wood floor, close to you. It wouldn't slide over here. It would slide close to you. It would take up it would shorten into something like a detachment fold. So, yeah. You know, on the time migration, we could see features that might be detachment folds, but we couldn't confidently interpret those. On the depth migration, that became obvious. As I go to the next slide there. There you go. There's the time migration and the depth migration. And see, it's these features down here, these things here. Yeah, it's almost hard to believe that that the same data went into these two images, but this is a much more obvious thing. So if I bring in the next little animation, so this is you have the competent unit and the incompetent unit here in this detachment fold. And this is a competent unit, and this is a competent unit. This Benton shale is pretty plastic and weak. So this is the detachment fold up here in the Niobrara Chalk. Pretty interesting to see. And that's something that, Ned actually changed. I'll show you here. This was Ned's original interpretation. And you can see he put this ramp, this Livingston fault, and he puts the detachment, where this fault comes up, he puts it much higher up in the Pierre Shale, which is a fairly weak unit above the Niobrara. If I go to his interpretation after the depth imaging, unfortunately he used the look of his interpretation is different, but I can tell you, he moved his detachment about 1,500 feet to 2,000 feet down. Instead of having the detachment go into the Pierre Shale, he goes much lower into the Benton Shale. That's a big change, and that changed. He could tell you more fundamentally how it changes interpretation, but that's a pretty big change in interpretation. And that was all due to the depth imaging. And before depth imaging, some of the features, why this is odd, I can't really say. Again, that's more Ned's bailiwick, but Ned considered what I circled here in this oval an odd interpretation. And after the depth imaging, he said kind of what's going on, especially right here. See these two lines here? These are actually two wells. These two wells drilled into this section here and actually produce oil and gas, I believe out of the Dakota. These two wells drilled and they found some repeated section in there. So to kind of explain what was going on in those wells, it became a lot more easy to do that with the depth imaging. Okay. And I'm coming up in the last slides here. I'll just show you some work I did in 2016. Just a few more slides. Kind of all the intellectual property of a depth imaging project is contained in the velocity model. And I show this velocity model, and it's just a bunch of colors on a screen. It means nothing to you. There was a lot of work, a lot of collaborative work between myself and Ned, back and forth between the geophysicist and the geologist. He would tell me a geologic constraint. I would see if it improved the data. This 17 iteration feedback loop that took like a couple months. But anyway, this was the velocity model that I obtained in 2014. After some subsequent work in 2016 using a tomographic velocity update, we were able to change the model a bit. Subtle changes to the audience, but as you'll see, it caused some significant changes to the depth imaging. I'll go to the depth image, the 2014 depth image, compare that to 2016. So I'll use a different algorithm. I'm not going to go to the differences between those. I can offline, but I'll flash back and forth. So subtle changes to that velocity model caused some pretty significant changes to the imaging, especially up in the shallow section there. You see those reflectors up shallow are much better imaged, and then some features down here, kind of in the meat of the thrust, are more continuous. And there's some places, actually Ned prefers the old image. So who knows? Okay, so in closing, I'd like to thank certainly Ned Stern. He's been a big guy in the Denver area for structural geology. He puts out a guidebook and a field trip study. He uses some of my work. John Crowther was one of my collaborators on the seismic processing side over the years. Randy Ray, I don't know if you know Randy Ray from the AEPG. He was kind of a luminary in the AEPG. He passed away a couple of years ago, unfortunately, but he helped out with the first generation of this. And over the years, I've had a lot of people give me constructive and tough feedback. But anyway, that's all I had, and I really appreciate your time.
questions for Morgan?
Yes.
When you said the feedback, are you saying you make an image and then you try to determine what the velocity field should be, and then you make a new image and then you recalibrate the velocity field?
Yeah, exactly. Exactly. And in a lot of cases, when it's three-dimensional data, really high-quality modern data, more of that work can kind of be done by the geophysicist in-house. But when you're talking about really tough geology, poorly constrained data, there's the interpretive constraints on this velocity model are huge. So it would be a matter of Ned would provide me with a feedback or a geologic constraint, and I would test it. And did it make a plausible or a better image? If yes, then we might accept the change. It was a tough process, but a fulfilling. I think it was a process that could really bear amazing fruit if it's done correctly.
Do you ever run into the problem that the answers are not unique, that maybe there's two answers that would satisfy the data?
Oh man, there's probably more than that. I would say that the geophysics is probably easier than the geology. I'd say the geophysics is, because the geophysics, like for instance, I can give you a concrete example. Ned was looking at the image over here. And remember I said we're missing like 3 miles of data over here. And he said, I've interpreted the ramp doing this. But it makes me, I have to make some weird assumptions about tension in the basement. He said, is it possible that it's really doing this? I said, yeah, sure, it's possible. We're unconstrained over here. We have no data illuminating this area. It could be whatever you want. So a certain part of it is, and that sounds trite, but a certain part of it is him asking me, where is the information better constrained? Like, where do I, in terms of confidence, where's my, and I can quantify, I have many ways to quantify the reliability of this image. Generally speaking, out here in the basin, very reliable. The velocity structure is simple. Over here, more complicated geology, a little less reliable. So we have to rely on, to knowing whether we're got a good image or not. It's a little bit harder. So anyway, it's a nonlinear process, and there's no single silver bullet. Yes. Oh, sorry. Yes.
Yeah, as I understand it, in the 50s they were dumping nuclear waste down Rocky Flats holes and caused earthquakes. And I'm wondering how you're applying all this to that.
Well, that was, as I recall, that was, I think that, was it Rocky Flats or Rocky Mountain Arsenal?
Rocky Mountain Arsenal.
Okay, yeah, they were injecting wastewater from, I don't know what the wastewater, I don't know if it was nuclear or not, but yeah, essentially they were injecting wastewater into one of these deep sections, and what it did, it literally lubricated some of the basement faults that were stuck and caused the basement faults to slip. There's an example out in the Paradox Basin in Colorado where the Bureau of Reclamation, so I have to go into some geology. There's a feature called the paradox salt, a salt layer, and in the Dolores River watershed of Colorado, that salt layer is exposed at the surface, and there's a small stream that cuts it and dissolves a huge amount of salt, and that salt then dumps into the Colorado River system eventually. So the BOR decided they would divert that salt water and dump it into a 17,000 foot deep well, and injected at very high pressures, and they were inducing earthquakes 20 miles away along that fault. So yeah, that's there's really nothing to do with nuclear. And here in Oklahoma, have you heard in Oklahoma the earthquakes that they're having there? Those are, I don't know, I mean, I've been in the oil and gas business my whole working career, I'm not like a cheap apologist for them, but anybody who says oil and gas industry is not causing those earthquakes is smoking crack. The problem, they started drilling these wells about 7 years ago that make about 95% water. So they'll pull out 400 barrels a day of oil and like 7,000 barrels a day of water. Now water's got to go somewhere. So there's a deep layer called the Arbuckle limestone down here that actually it's under pressured, so they can just dump the water in and the formation takes it. And they dump huge volumes of water in, and it's absolutely inducing earthquakes. This when you change the pressure situation around that fault, it causes the faults to.
So how does your work connect with that or apply to it?
Yeah. So
Morgan,
yeah.
while we're talking about this, can you go back to your best model, structural interpretation of seismic?
Sure.
We can kind of think about how
That one.
Yeah, we can start thinking about how the fluids might be moving.
Yeah, and for instance, so the Bureau of Reclamation, they're under some heat for inducing earthquakes. And the question is, they want to continue their program of injecting wastewater. They want to be able to do it in a better way. So in order to do that, they need to know where the basement faults are and stay away from those. So I would say that if you just kind of go to some of the comparisons of the time versus depth. Like for instance, boy, do I have an example of a fault? These faults, these are faults over here. They're kind of out in the easy area, but they're kind of crisper than they are on the time image. So you're kind of looking for improved interpretation. Can I interpret where the faults are? That's a typical uplift from the kind of work. This is not the best example to show like improved imaging of deep basement faults, but I could go into my computer there and pull out 10 of them that do show that. But yeah, in a nutshell, if you're trying to, if you're worried about induced earthquakes, you want to get a better picture of where basement faults are and where faults are in general. And,
on this image,
yep.
roughly where were they injecting whatever they were injecting in? Secondly, where was the groundwater?
Well, I think the real question for the Rocky Flats guys was like, I'm trying to think how shallow that is. Let me go to the one that has a depth scale. Sorry, I have this habit of cutting the. Oh, come on! I know it's there somewhere. Hold on a second. Sorry. Let's do some editing. Let's just bring this to the front. Oh, it doesn't have that. Where's my depth scale? Huh. Right click doesn't work. There we go. Oh, weird. Okay, sorry. I don't know. All I was trying to do was get the. Whoa! Come on. Whatever. Yeah. So. Yeah, this fault here. The question was, the faults like this, do they extend all the way to the surface? That's really what they were trying to answer. I'm not sure what they were doing at Rocky Flats in terms of disposal. I think it was more shallow burial and probably some leakage. Whatever containers they had the nuclear waste in was either barrels or. It's going to leak. The question is, when it leaks, is that water going to percolate down a fault system and get into whatever the aquifer is? And I wish I could tell you which layer was the aquifer, but I don't know. Yes, sir.
Yeah, I have a question. I kind of remember the Rocky Flats. They did a lot of triggers.
Yeah.
And so was it tritium in water that they were putting down, or it wasn't so much? I mean, it has to do with waste, but it wasn't like heavy-duty plutonium. A little short-lived. Does that make sense? And how does that relate to what you're trying to do?
I'm deferring to you on that. I have no clue. Yeah, I don't know. I know they had a reactor there. they had a near meltdown in like 67 maybe. There was almost a very near significant, so I don't know what they're using that reactor for. If they were using it to get...
They made plutonium injectors for the pumps.
Okay, okay,
Yeah, that's what
okay, okay.
But it was with plutonium rather than...
Yeah, well, maybe it was both.
Oh,
But plutonium's really bad, so that was why it was so nasty.
And whatever shenanigans they were up to at Rocky Flats are above my pay grade. I just mooch their data and make some bad interpretations of it.
You want to worry about that kind of problem. You don't want to be in Washington because Hanford, out there where they were doing all the nuclear stuff during World War II, they buried it all in metal containers, single metal containers. And that stuff is now in the rocks, going through the rocks, percolating towards the Columbia River. And you want to talk about some seriously nasty fluids. And I was amazed. I sat through a lecture about how they were very carefully monitoring where this was and all this. And I finally had to ask the question, well, is anybody trying to think of how the heck to stop it?
I heard a story about that from a guy who thought they could glass, form glass around it. Does anything you remember that?
No, I have not heard anything other than the technical talk. I was sitting there going, hey guys, we can drill a line of wells and put some pretty serious cement kind of stuff down there that at least would slow it down. But I mean, this is all, less than 2,000 feet down and it's just headed towards the Columbia River. So I told my wife she loves salmon. If it ever gets to the Columbia River salmon. The question on the modeling.
Oh, yeah, sorry.
When we talk about velocity,
Yes.
did you actually include density in the imaging?
No. We that would be more under the lines of like a waveform inversion to actually use the density. Now we can certainly, you look at the strength of it. If you try to relate the strength of the reflection, like some of these reflections are not caused by discontinuity in velocity, or they could be, a reflection is caused by a change in VP, VS, or density, any of the three. And you can actually study how if I go back to the plot that over here, I didn't intend to go down this. This is definitely another rabbit hole, but I won't go too far down the rabbit hole. Oh God, too many slides. Yeah, this one here. So you can see here that we've got one shot and multiple receivers, and the receivers that are close to the shot, the reflection happens at sort of a small angle. Out here it happens at a large angle, and you'll see the strength of the reflection change as a function of what the illumination angle was, depending on some of the details of VP, VS density above and below. So you might say, oh, why do I care? But like a hydrocarbon bearing sand sometimes will show an anomalously low VP relative to something, a gas sand versus something saturated with water. So you can actually differentiate a rock filled with gas versus a rock filled with water. It's kind of amazing. And it's not just a small effect; it can be a big effect. So anyway, yeah.
This is a really handy slide. This shows just one shot. What they really do now is they'll take a shot and then move over to about 2 geophones and take another shot, move over 2 geophones, take another shot. So if you think about what's going to happen in the ray tracing, you're going to get 8 to 10 different images of the same subsurface point. So John, this goes back to your question about how do you figure out what the velocity field is. Well, they come at it at a series of different angles and they can begin to get at the velocity field.
Yeah, yep.
If you wanted really good imagery, you also have to deal with the density. For example, on this little cross-section, there was carbonates and stuff down there. Those are a whole lot harder and faster than stuff above it. And that bends the seismic energy just as well as the velocity.
Question about who funded this work? Was it just a science project, or was there a...
Science project.
Yeah, so you just did it for fun?
Yeah, no, I think we, Ned had consulting clients, and I was probably fully employed at the time or consulting, so yeah, we just did it for, when I was out selling stuff, I could go and take this and show it to people and highlight depth imaging technology. Nowadays, I just do it for fun, but yeah. Oh, yes, sir. Yeah.
You talk about how the stiffness of the rock affects the velocity. Does
Yep.
rock stiffness change with depth? In other words, if one layer of limestone, granite, whatever,
Yeah.
is the stiffness the same at the top as it is 1,000 feet lower?
Yes and no. Some types of, most rocks, most of the rocks we deal with, they absolutely, as you bury them deeper, they get stiffer. And what happens is really the pores, if you take imagine a sand grains, up at the surface, perfect sand grains, I believe, are about 37% airspace and 63% quartz. As you go deeper, the grains kind of get squished together and the porosity decreases. So the density increases, the stiffness, the grain to grain contact improves, and the rock gets more competent. As a general rule, the deeper you bury a rock, the stiffer it gets.
So you have to accommodate that in the model.
Yeah, and actually, so it's you asked. You asked.
Will I regret?
No. It's okay. So if I go to the final velocity model, this is stuff that's near and dear to my heart. So, okay, so out in the basin, you got flat. It's pretty simple geology. Okay, so if I go back to the velocity model, notice how, if you start at the surface, you start at about 7,000 feet per second, and down here we're kind of not linearly, but pretty linearly increasing to 15,000 feet per second. It's doubling as they go down in depth, down to 10, 11,000 feet. And that's what you'd call a compaction trend, just deeper, assume it's the same lithology, you just bury it deeper and it gets more compacted. But it's interesting, how you'd say, well, as I go up the basin here, the question is, now I've got rocks here that have been uplifted. They were buried once, now they've been uplifted. Now what is the velocity? You'd say, what does the velocity do now? You might be tempted to say, oh, well, they'll retain their same velocity as I move them up dip. Sort of, but so I know the slide to show. I know the one to show. There we go. Okay, notice I'm in the shallow section. Look how see how the bed. So if this was perfectly, if the velocity was perfectly following structure, it would be kind of like it is over here. Up in the shallow there, you notice how the contours of that velocity model are kind of cross-cutting the actual seismic dip. So there's sort of an effect where as you uplift the rock, it doesn't exactly preserve the velocity. It was down deep. It sort of relaxes a bit. It's a strange effect, and I'm not sure it's all that well quantified, frankly. But you might ask, oh, well, is that just a cosmetic aspect of your velocity model? No, actually, I had to do that. It required a lot of work to figure that out. I wanted to just have it follow structure. They didn't give the best image, and you could absolutely tell it was not giving a good image. There were definite structural distortions in there. So it's a very interesting. It's a good question. So it's the deeper you bury them, the faster it gets. When you bring them back up to the surface, they mostly retain their deep velocity, but they lose some of it. I don't know if anybody else has any deeper insights on that, but I've observed it here.
Yeah, no, you can see it.
Yeah.
How deep can you actually go down with a wave and back up?
Center of the earth. Yeah, with earthquakes.
Yeah, earthquake.
An earthquake in Indonesia as a ray path, as it goes way deep and comes back up, we pick it up on the seismometers here.
How deep?
Well, the stuff, the kind of studies here, boy, it's you get energy down, and a lot of it's limited by how much recording time you have. You have to keep, if you want to image at 50,000 feet, you've got to record enough data to go down there. I would say here you could probably see. Well, part of the problem is there's not too much to see down in the basement. They're up here. We've got these different layers, which were sedimentary layers deposited in a shallow sea. Down in the granite basement, you might be some basement faults, or maybe there's not a lot of recognizable reflectors down there. So even if I could see them at 25,000 feet, I might not be able to recognize it as an actual geologic feature. Certainly, I've seen stuff in the Powder River Basin. I remember seeing a crazy, I was telling John Heberger this earlier, I believe it was some ancient intrusion, or maybe even a plate suture or something, I don't know. You could see a distinct reflection at like 35,000 feet. Way below sedimentary basement. It was crazy, but it varies. Out in the Gulf of Mexico, you could the stronger the source, the longer the recording time, the deeper you can see, but the lower the image quality. It's just harder. The longer those waves have to travel, the harder it is to get a coherent signal back. But
I might just add that these are real problems that people are have at least spent millions of dollars on trying to sort out, because there's oil and gas that actually is discovered underneath mountain fronts. So a good example is over Madden Field over on the south side of the Owl Creek Mountains. It's one of the larger gas fields in Wyoming, and it's down, I think it's around 25,000 feet, something like this. It's well over 20,000 feet. And it's a very large gas field, and they were dealing with these velocity problems like this to try and put multi-million-dollar wells in the right spot, because if this wasn't figured out right, every one of those wells would be a dry hole. It would be a waste of many millions of dollars. So it's a real economic problem, and there's not a lot of overhang here, but there are places, you can look at a cross-section on the wall over there, and actually the granite that is shown on the right-hand side, which is the Gros Ventre Mountain uplift, is actually, it's too steep. There's actually several miles of sedimentary section underneath. If you started a well in granite, you would go out of that granite and down into Cretaceous shales and sands, and those are what produce a whole lot of gas, mostly down in the Pinedale and Jonah fields. And I've said it jokingly many times, there may be a giant gas field underneath the town of Jackson, because that cross-section goes through the town of Jackson, through us right here. And there's 25,000+ feet of sediment beneath our feet right now.
Nice structure, too.
That are possibly oil and or gas bearing.
Yeah, and John, I actually, very early in my career, I actually did some mapping on that. And the problem he was showing you tonight was exactly the issue we were dealing with, because if you started at the surface, the first thing you had to drill was about 2,000 feet of volcanics. Very fast, very stiff rocks. And then that was basically, below that was this huge upthrust that had been eroded off before the volcanics got in there, and you were drilling into the erosional remnants. And the rocks were literally upside down. As they were eroded off, they're deposited, so everything was kind of velocity and density was just the reverse of what you would think it would be. And you can spend a lot of time trying to figure out what the velocity and density model is to try to get one of these things. Just a little tidbit, oil and gas brought you, or the geophysics in it, brought you a number of things. One is analog to digital conversion. In the old days, all the seismic was done with just analog, and really, really tough to work with. So the oil and gas business went to Texas Instruments and said, hey, we want some way to digitize those curves. And that's came out their chips to do that analog to digital conversion. Well, now, that's, when you talk to Siri, that's what's going on. Your voice is analog, it's being converted to digital, and it comes back the other way. And the other thing I'll comment on is when you look at seismic data like this, you couldn't do it without huge computers. I was involved in '92. We bought the first massively parallel computer in the oil and gas business. We installed it. It could do 80 billion calculations a second. And our typical, and these are three-dimensional problems, so we have 3D. We started off with about 5 trillion data points. Think of it as a pixel in your photograph. And then you go through the time and depth migration process that he was talking about here. And typically that would take about 6 months on that computer to reconstruct the whole 3D survey.
Not so long.
About 6 months.
How long does it take?
You can,
Every oil and gas company have
10 minutes.
geophysics mathematicians to create this model. Seems like a little bit of a waste, but
That's the competitive edge, you know? Come on. And your question.
I would if I was selling it to you.
And you talk about, or John asked the question about it, can there be 2 interpretations? Up there at Owl Creek, where the Madden Deep is, I literally was on structural school, and then we had 3 instructors looking at exactly the same rocks, and those guys argued for over 30 minutes on 3 different interpretations of the rocks we're looking at. I get it.
yeah.
More questions?
Good
Okay,
questions.
well,
No, thanks.
thank you, Morgan. That was an excellent presentation.
Appreciate it.
We have a little gift for you.
Awesome.
And I will personally commend you on your PowerPoint skills.
Yes.
Because that was fantastic.
Oh, thank you very
And
much.
I know personally how much time went into putting those animations and things together, so thank you.
Especially the reconstruction.
Yeah. Very impressive.
Never